quietly and in a civilized manner and go out into the piazza until someone tells you what to do next. So, well, here we are, January, New Year and all that. I have to start with an apology of sorts. Our December talk had to be cancelled. I'm very sorry about that, but it was entirely out of our control. COVID was raging through the RAS staff and we had nobody here to look after the building for us. So I'm afraid we had to cancel that talk. Everyone's now back in business and recovered, which is good news. But it was a shame about the talk because we had in mind a sort of Christmas party with a library tour and some Christmassy refreshments. So I'm sorry you missed out on that. The talk itself, which was by Professor Nick Achilleos about giant planet magnetospheres, Jupiter to you and me, that will be rearranged, although I can't promise mulled wine and mince pies for that. I couldn't possibly comment. People online won't have heard the question, so we'll avoid that. We might have Easter buns or something. Anyway, so today's speaker is Professor Alberto Vecchio of the University of Birmingham, where he's Professor of Astrophysics, he's Royal Society Wolfson Fellow, and he's the founding director of the Institute for Gravitational-Wave Astronomy. He's also held positions at Cardiff University and the Einstein Institute in Germany. He's a member of the LIGO team that detected gravitational waves in 2015 and has been honored with several awards and prizes, including being co-recipient of the prestigious 2016 Special Breakthrough Prize in Fundamental Physics. And he's going to tell us today about LISA and the next stage of gravitational wave astronomy. And I should say he has to leave at 2 o'clock, so get your questions in after the talk. Thank you. Alberto.
Thank you. So thank you very much for the invitation. It's a real pleasure to be here, and I apologize for having to leave at 2 o'clock. I messed up my calendar because I'm giving another talk at the Institute of Physics at 2:30. That's the reason. So I'm going to be talking about the Laser Interferometer Space Antenna, LISA. This is an ESA mission with a 20% contribution from NASA. It's what is called in the ESA jargon an L, meaning large, meaning expensive mission. So this has been, let me try to find here. This has been in the making for over 30 years. So this is the very first proposal, 1993, that was put together by a number of people here, and you can see a few famous people from the UK, for example, Jim Huff and several people in Glasgow. There is Mike Cruz here, who is the person who hired me in Birmingham and was a Royal Astronomical Society director. At that time, he was at trial. And this has been going on for, as I said, over 30 years. And it is a very important point in time for us right now, because next week on Thursday, there should be the big announcement from ESA that what is called the multilateral agreement, essentially all the funding agency, signing the checks to actually fly in the mission, they'll make this announcement. And so the mission really becomes a real mission with the money there, and it's a lot of money, and I'm sure a bit more money is going to be required. The mission, however, is going to fly in the mid-2030s. There is a lot of work to be done in preparation for this mission, and I think everyone in astrophysics, cosmology, and fundamental physics, regardless of the area they're working on specifically, regards this as really a transformational step in our exploration of the universe. So I'll try to tell you why we think this is going to be such a transformational mission, why it took so bloody long to get it done. And there are two elements to this. One, I think, is psychological. I mean, this time do gravitational waves really exist? I mean, was a big issue. And the other point was, well, we are pretty sure they exist. However, the technology in order to do detections and even more to have an observatory to use gravitational waves to really observe the universe was an enormous question mark. And people really thought they couldn't do it. Okay, so in essence, in essence, what LISA is a gigantic ruler, okay? So assume that what you want to do is to take 3 bricks, put them in space, and then measure in real time the separation between these 3 bricks, okay? And you say, well, this is pretty dull. That's true to some extent. However, again, the maps. Then the next step is that you want to measure the separation of these bricks with that level of precision. This is called 1 picometer, is 10 to the minus 12 meters. It is the size of the of 1 atom of helium. Okay. The next problem is that the bricks are not sitting next to each other, but they are 2 million kilometers apart. Okay. And so people say, okay, you want to build a ruler, we have rulers, you want to do these ridiculous things, clearly this can be done, go away and do something else. Okay, so that's in essence. And so that's why it took so long. So the reason why people wanted to do this, this kind of experiment or build an observatory, which is built on this technology, of course, goes back to Einstein's and his theory of general relativity. So 1915, we know that Einstein changes our view of how gravity works. Newton's theory is an approximation. The true description of gravity is actually something else, is general relativity. And the idea is, in the famous work by Wheeler, is that space tells matter how to move and matter tells space how to curve. Am I doing a mess?
No, I'm just going to get rid of this.
Oh, I didn't notice this. Perfect, thank you. So this idea of this very strong link between geometrical description of gravity and the actual physics. So the Earth goes around the sun, not because there is this force, as Newton had it, the action at a distance, but simply because the sun, having mass and energy, will curve space-time, and you throw a ball in a linear trajectory on this curved space-time, and the ball will orbit around the sun. So we all know about the big revolution of this theory that nobody could quite understand at the very beginning. And there is a fundamental prediction of the theory. And the fundamental prediction of the theory is that if you take masses and you, let's say, accelerate masses, in this case, there are 2 masses going around each other, then they will radiate energy in the form of these ripples of space and time that travels essentially undisturbed throughout space and time, the universe, telling information about what is the source. And so for the purpose of this talk, then gravitational waves are a messenger of whatever masses are doing throughout the cosmos. One of the reasons many people got into this business, including myself, was to use this new form of radiation to making exploration of the universe, not through the atom molecules and so on that radiates electromagnetic waves, but looking at what people call the dark side of the universe. So now, if you think that then observing gravitational waves is important, then you need to design an instrument that that is able to do so. And this will go back to the bricks I was showing at the very beginning. We now do these exercises in undergraduate physics. So the Gedanken experiment is take a ring of particles in a complete if you want, empty universe where you have only this ring of particles that are freely floating, and then send some gravitational waves through these rings of particles. And what's going to happen is that this ring will be stretched and squashed by these gravitational waves. And the stretching and squashing of these gravitational waves then tell you about the structure of these waves and the sources that generate gravitational waves. So the recipe then to observe gravitational waves is really to build a ruler that is able in real time to monitor what is the stretching and squeezing of some particles that you are able to have freely floating. Now, I'm moving too much, surely, around. So I'm moving the mass of my body. I'm radiating gravitational waves. Nobody here is feeling, the stretch and squash of space-time, because the effect of gravitational waves is minuscule, is really minuscule. And so this is, in fact, Einstein said, this is my prediction, I'm right, my theory is perfect. However, forget about detecting gravitational waves, because this is not going to be possible. In fact, nobody really touched this prediction in 1916. This kind of area of physics for at least 50 years. Nobody really touched anything to do with general relativity for 50 years. This is a letter that Richard Feynman, one of the greatest minds in theoretical physics of the 20th century, sent to his wife when he was invited to go and went, and clearly he regretted he went, to a famous first conference on gravity in 1962. And you can read this, but essentially Feynman said, this is boring, okay? People here are talking nonsense because either they're trying to do something which is trivial, or they're trying to do something which is impossible, and this is wasted effort, okay? So remind me not to go anymore to any gravity conference, okay? That's it. And, but this is the time when people really started to think about putting together some experiment about gravitational waves. And the idea is related to, can we engineer some technology that allows us to measure this changes of separation of, let's say, freely floating test masses of bricks, okay, at this level of precision, which is phenomenal, okay? And for the case of LISA is 2 million kilometers, and you want to see how much these masses move by, the size of an atom, okay? And you may think that the masses are made of atoms. Therefore, the atoms are going to move by at least, the amount of, which is comparable to their size. And the key game changer was really the laser technology, which is at the heart of many of the discoveries that have been done in the past 5 or 7 years. So this is a movie that was produced by LIGO when there was the first detection of gravitational waves. LISA works in a conceptually, if you want, identical way, but in a practically different implementation. But the idea is you have these 3 test masses, in this case mirrors. You shine a laser beam. The light is your ruler. As gravitational waves move these test masses, the intensity of light will change. And as you recombine the light here at the center, depending on how much these arms have changed in length, you will have a different intensity that will allow you to do this measurement. So that was the key cornerstone idea in the 70s and then late 80s that led to the design of gravitational wave instruments on the Earth, and then the design of a larger instrument in space. Okay, so this has been applied on the Earth. So this is the Earth-based version of these gigantic rulers. Those two are the two LIGO instruments in the US. These are 4 kilometers in size. There is it is used to be a French-Italian instrument, but is now includes many more countries. In Europe, this is the Virgo detector, essentially the same thing. In the outskirts of Pisa, in Italy. No, wrong button. Hold on. Let's see. Sorry. There is now a version in Japan, Kagra. This is an underground instrument that have started to operate. So there is this flourishing of activities here on the ground, and these have led to the detection of gravitational waves that has been celebrated, in 2015. And the only thing that I'll play the movie, and this is the movie of the first two events that LIGO observed. What is plotted here is the intensity of the way in a plane that is time versus frequency. And the two things you should notice are the axis, the time axis is in seconds. So these are short, order of a second or less. And the other important point here is frequency is about hundreds of hertz. So these are very quick, very short events that happens at frequencies that are about 100 hertz or thereabout. And these are due to binary systems of two black holes, about 30 solar masses each, that are colliding. Okay, so this is great. The discovery of gravitational waves, New York Times magazines, and so on. But what is really important is, for the first time, we detected gravitational waves, and we were able to start exploring new objects in the universe. At that point, we didn't know binary black holes existed. We thought they would, but there was no proof. The other interesting thing that you may have heard about is that LIGO also detected gravitational waves from colliding neutron stars that also were picked up as gamma ray bursts. So these are what people call kilonova, and they are now studied as the sites where we build the heavy elements in the cosmos. So this has been going on for a while with these experiments on the ground. This is just the latest catalog, is about 100 events. Okay, so now we're really doing these new explorations of systems that are between about 1 and 50 or 100 solar masses. And LIGO is operating, and we are detecting one of these guys every day, every other day. So this is great. There's something exciting that is also happening, or has happened recently, and is that one can use the extremely accurate timing of pulsars, of radio pulsars. They are cosmic clocks. They send you a pulse of radio waves at incredibly exquisite precision. And they can be used to look for gravitational waves. And they have, through a network of radio telescopes all around the world, and we had results coming out in last summer, where 4 different collaborations, I'm part of the European Pulsar Timing Collaboration, we saw some initial evidence of gravitational waves, not from black holes of 10 or so solar masses, but from the giant black holes, let's say 10 to the 9 solar masses at the center of galaxies. Now, so what is the lesson here? So this LIGO works at about 100 Hertz. This pulsar timing array works at much lower frequencies, about 1 nanohertz. And they are telling us something different about the cosmos, the object of the cosmos, which we know from the wonderful observations we've done with telescopes in many different bands. This is the radio, the optical, the gamma ray, the neutrino sky. And they really look different. Every frequency band is telling us something about different phenomena in the universe. The same thing is true for gravitational waves. And if we have this observation at very high frequencies with LIGO and this observation at very low frequencies with the pulsar timing array, it has been recognized, it was recognized 30 years ago, that there is a frequency range which is about 1 millihertz, in which the sky could be extremely rich of sources that radiates gravitational waves. And this really drove the concept of LISA. So we know from observation of galaxies that galaxies, probably most galaxies harbor black holes at their center, and that galaxies interact with each other. Now, how we assemble galaxies and the black holes through cosmic histories is one of these big mysteries. We've seen this recent JWST observations of galaxies at black holes very far away from us at very high redshift, very early on in the history of our universe that we didn't expect to be there. So we think galaxies and massive black holes build up very early on. And then as the universe evolves, these galaxies will interact, will bring together the massive black holes. The massive black holes will form binaries, and these binaries become gravitational wave sources. And we really cannot trace, looking at the black holes, this crucial evolution in our universe. We now have these wonderful observations, for example, of the black hole at the center of the Milky Way. We have the famous Event Horizon Telescope, shadows of the black hole in our galaxy, and here at the bottom of M87. But of course, we never see the black hole. We just see the effect that the black hole has on the intervening matter. So can we build an instrument able to do, to actually look at the black holes? So this is, okay, the L has been cut out, but so that was really the driver to put together this LISA mission. Can we trace the history of assembly, interaction, formation, evolution, etc., of the massive black holes at the center of galaxies by looking at the black holes, not at the galaxies and the effect of the black holes? So this and these binaries emit, when they merge, at about 1 millihertz. Therefore, we need to build an instrument able to look in that frequency band. LIGO cannot do it. Just everything shakes on the Earth by the time you get to about 1 hertz. So one had to go in space. There was no way. But of course, one has to go in space, and one has to build an interferometer with an arm length that is much larger, because the waves have very long wavelength, than the one on the ground. The only advantage to do this in space is that space is essentially empty, and so the vacuum system, you get it for free. Everything else, it's terribly expensive and challenging. Okay, so in essence, here's the mission. So LIGO is an L, or all the instruments that we have on the Earth are Ls. for LISA, for a number of reasons, we have a triangle. So essentially, we can build synthetically two L's in the same place. But it's an L, so it is this triangle of 2.5 million kilometers. It is sent in an orbit which is trailing the Earth on exactly a 1-year timescale. Is sent on this orbit trailing the Earth, just behind the Earth, for two reasons. One is that you need to be sufficiently far from every single mass because the mass will disturb you. At the same time, you cannot put it too far away because otherwise telecommunication, you record all the data, but you cannot send them down to Earth. So it's this gigantic triangle of about 2.5 million kilometers on this orbit. Here's the triangle. And then you have laser beams that are sending signals from the heart of these spacecrafts. And the spacecrafts are just shields. They play no role whatsoever, is what you do not want, apart from shielding really the core of the instrument. So this is a spacecraft. So there is the spacecraft are about 2.5 meters in diameter. So they're not that big. So you have these laser beams there. But what is crucial are these blue cubes. Okay, these are test masses. They are gold, platinum, 10-ish or so centimeter cubes inside the spacecraft. There are 2 of them per spacecraft. And what the mission does is we really monitor the change in the separation of these cubes for years and how they move with respect to each other. And what the spacecraft has got to do is that just to move a little bit around these cubes to follow them and shield it from, for example, you know, the solar wind, and then provide telecommunication systems down to the Earth. So the cubes are supposed to freely fall in space. And then the spacecraft follows the cubes. How the cube moves with respect to each other is the change of the arm of the interferometer, and everything else is engineering to keep them, you know, freely falling as quietly as possible. And everybody said, this is the key piece of technology that we can't guarantee is going to work. Because the level at which these things needs to be freely floating over years is just impossible. And I'll tell you what was done to convince everybody that this can be actually done. So this is the LISA science. This is a technical plot. I'll show it here once, and then I'll show you a few things about the specifics. But this dashed green-black curve is it tells you how sensitive the instrument is. What is above this curve is a source that can be seen. What is below is something that cannot be seen. On the vertical axis, there is the strength of the waves. And on the horizontal axis, you have the frequency. And you notice the frequency here is a fraction of a hertz. So it's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. These are phenomena that take place on time scales of 10 seconds, 100 seconds, 1,000 seconds, minutes, hours. So LISA is a binary systems discovery machine. Okay, the tracks that are in red are black holes of different masses, essentially throughout the universe. So LISA will be able to see pretty much the entire massive binary black holes in the universe. I'll show you a plot later on. All these dots, blue dots, are binaries of what are called white dwarfs. These are dead suns, okay, in our galaxies. And there are so many of them, and although they are little and not too heavy, there are so many of them that actually they will produce so many gravitational waves that they will be above the limit or the sensitivity limit of the instrument, so that they will be a foreground, something that people do not want to have. So what was done to convince the European Space Agency and NASA that this was possible? So a big technology program was put in place, has a fancy name of LISA Pathfinder, okay, really to demonstrate the possibility of having test masses freely floating, freely falling over long time scales. So the LISA arm, which is 2 million kilometers, was shrunk down to 30 centimeters, and 2 test masses were put in this enclosure here that resembles the actual LISA spacecraft, but this is the LISA Pathfinder mission. And the idea was really to demonstrate that one could let these masses fall so quietly. So Pathfinder was launched in December 2015. This is the launch from Kourou. Now, this is the same time when LIGO detects gravitational waves, which is important psychologically. And then this is 2 years later. This is, again, is a technical plot, but at the very top are the requirements, how freely falling these masses needs to be. The black for this demonstration mission, the black line in the middle is what is required for LISA, and the dots and the red line is what was actually achieved with LISA Pathfinder. And on the y-axis is the residual acceleration of these masses. Now, these are funny units, so 2 things. First of all, the mission did so much better than was needed for the demonstrator, but even for LISA, okay? And to tell you how quiet the environment can be, the residual acceleration corresponding to this red line means that if you kick one of these masses with this acceleration, a year later, the mass would have moved by a few centimeters, okay? So it's a very quiet place. It's not perfectly quiet, but it's quiet enough by a factor of several. So these results, so LISA Pathfinder flew, performed spectacularly well, and then LIGO at the same time detected gravitational waves. This was the trigger. That's why, I mean, it was in some sense the right perfect storm. Okay, so I'll spend a few, the remaining time to tell you something about the science that we'll be able to do, because it's going to tell us something very different about the universe with respect to what LIGO is telling us. Is also going to require, and this is very much, in line with what our, I guess, government and all the governments want to hear in terms of, let's say, fundamental science, that we have development in technology, in this case is data analysis and artificial intelligence, that then will allow us to do this spectacular science, and we'll learn things that are going to have an impact on the broader economy. As I said, LISA is discovery machines for binaries throughout the universe. So the first thing that I would like you to show is, this is again the first LIGO detection. So you see the different panels. The top is from the LIGO Hanford instrument. The middle is from the other observatory, the Livingston one, and at the bottom, the 2 data sets are combined. The thick line is the actual data, and the thin line that you see there is the actual gravitational wave that we reconstruct. And the key point here is that the noise, the thick line, is, if you look towards the left in particular, is much larger than the signal you want to find. For LISA, the situation, I mean, this is not a fancy plot because we do not have fancy pictures, but for LISA, the situation is completely opposite. The instrument is so sensitive that essentially all the sources, many of the sources, will dominate the noise, meaning that actually what is going to be an obstacle to try to observe all these different sources is the foreground radiation from a lot of things you may not want. And also all these sources, you see the time scale, this is about a year. Okay, these sources, instead of the case of LIGO, when that are present only for a second, 10 seconds or so on, these sources are persistent. They are on most of the time. And this will create a big challenge. So in terms of things we will discover, as I said, the Milky Way is going to be very bright in gravitational waves. So you can see a plot here of the galactic disk and the bulge at the very center. This is full of all these dead stars, these white dwarfs that are essentially the end product of a star, of the life of a star like our sun, half of which are in binaries. There are about 1 million of these guys in our galaxy. LISA will be able to see 50,000 or thereabout. And they are so strong that they will dominate the LISA data set. So this is a new way of doing stellar evolution through gravitational waves. You also see stars here, and this is the cluster of what are called the ultra-dwarf galaxies that are part of our local group. I mean, we know the small and the large Magellanic Cloud, but there are many others. They have a chemical composition that is very different from our galaxy. We do not know what are really the stars that are formed there and what their end product is going to be. I mean, we know they're going to be white dwarfs, but by studying in gravitational waves, the white dwarfs of these ultra-dwarf galaxies, they just made it to be a galaxy. Then we can do studies of the chemistry of environments that are very different from our own Milky Way. This is the real key target. I mean, for people doing stellar evolution, all those white dwarfs are super exciting. For others, you know, the black holes at the center of galaxies, the massive black holes at the center of galaxies, like our own Milky Way, are the most exciting target. Again, this is a plot that shows you how strong is the signal. So red is very strong, blue is kind of strong, but not that strong. Everything here is observable as a function of the mass of the black holes. And this is from 1,000 solar masses all the way to almost 1 billion solar masses. And over there is the redshift, okay? So everything up to redshift 10, and actually I cut the plot. We go to redshift 20, 30, at some point the black holes haven't formed yet, okay? So we'll be able to see the entire universe. And one of the hopes is, can we see the first generation of black holes that are forming at the center of the galaxies? Now we need a few ingredients. We need the black holes to form, but also then to pair up. So we'll have to see. But in principle, we can see the entire universe. So this is one of the reasons why this is a mission that is so attractive for a number of areas of astrophysics. This is too technical. I'm gonna skip it. But let me just say that we will observe black holes that merge, that collide, and then we'll be able to tell if the black hole collides for conservation of linear momentum, the formation of the black hole that is the remnant will recoil with respect to the center of the galaxy. And now we have observations of jets or nuclei displaced from the center of galaxies. The guess is these are remnants of massive black holes that collided. And here we'll be able to see in which direction these guys are going and measure the recoil velocities are hundreds of kilometers per second. We'll be able to measure this and make these different connections. One thing that has become extremely sexy recently is again connected to what we've learned in astronomy, that if you look at one event in many different frequency bands or at many different wavelengths, you learn so much more, okay? The same thing is probably going to happen also with gravitational waves. We call it multi-band gravitational wave astronomy. So on the right-hand side is the sensitivity of what we have with LIGO. And on the left-hand side is the sensitivity of LISA. So the dot that we have here at the center is the strength of a binary black hole, of the first binary black hole we observed with LIGO, but actually captured about 2 years before it merges. And so what's going to happen is the following, if I can, okay. So you see the time. So LISA may pick up this signal, you know, sometime before it merges. And slowly, one will be able to watch as the radiation brings the two objects closer and closer together. Therefore, the frequency increases. And this will last a couple of years. And then we have no instrument in the middle that is going to be able to see anything. And it's going to take about 2 weeks for the binary to shrink even more and then enter the LIGO frequency band. And then at the very end, the final half a minute, LIGO will pick it up again. And by putting together this different information, essentially we'll know every single thing you need to know about this binary. And one of the reasons why people are interested in doing this is that it's still a mystery what is the primary engine, astrophysical engine, to produce all these binary black holes that we observe with LIGO. It's not clear whether it is all from stellar evolution, whether we have dense star clusters, whether AGN disks are playing a role. This is going to allow us to do all this kind of astrophysics. And the final thing is connected to this picture. And I think this is the holy grail, really, for people doing this kind of work. And I'll probably will be dead before what I'm about to tell you is going to happen, but maybe not. Let's see. So this is a very famous picture. This is the cosmic microwave background. And this is the earliest picture we have of our universe. Our universe was 300,000 years old. We cannot go beyond this simply because photons interact with each other, and therefore we know nothing prior to this. The photons interact a lot with each other, but gravitational waves don't. And this is one of the problems we have in doing gravitational wave experiments. The waves interact very little with our instruments, but they also interact very little with everything else in the early universe, which means that, you know, the Big Bang, whatever it was, that was a source of a background of gravitational waves. And so the holy grail is if we can detect the cosmic gravitational wave background, this will allow us to see all the way back until the universe was a fraction of a second old. And I'm sure that would revolutionize what we know about our early universe. I have no idea what's going to tell us, but that's the ultimate goal. Lisa will have a go at it. I don't think it's going to succeed. Possibly, we'll need probably more instruments, more sophisticated in the future. But being able to take, let's say, a picture when the universe was a billionth of a billionth of a billionth of a second old sounds quite interesting. So I'll stop here. We have many instruments doing now gravitational wave astronomy, and I think if you are young, it's a very exciting field. Thank you very much.
Thank you, Alberto. Quite interesting. I think that sums it up very well.
Okay.
Questions, please. As I said, Alberto has to leave at 2 o'clock, so we haven't got very long, but
Yeah, thank you for a great talk. 2 questions spring right mind straight away. One, any thoughts about changing the baseline so that you can change the frequency response and coverage, especially for that gap in the middle? Secondly, just came into my mind is, how on earth would you know that a gravitational wave came from before the 300,000 years? Is there a redshift? Are gravitational waves redshifted?
Okay. So the first question, changing the baseline, the answer is no. And the reason is that this is related to money and engineering. There is a program. There have been many, many studies about changing baselines for the next generation, mission, Horizon 2050, something like this, Vision 2050. There are proposals to have both shorter baseline or longer baseline, but for this mission, this is it. Regarding your second question, gravitational waves are redshifted exactly in the same way as the electromagnetic waves. So the photons and, if you want, the gravitons are massless particles, and so they behave in this way, in the same way. So there's going to be a redshift. Being able to tell that there is a cosmic gravitational wave background from signal processing and statistics is not going to be simple at all. Okay, you have to say this is the noise from the universe. This is the noise from the universe, from the instrument. What I didn't say is that LISA has 2 things which are important for this. First of all, it's a triangle, but really these are 2 instruments that are actually, so it's a triangle, but you can synthesize, if you want, 2 instruments that are L's in the same place, but with different orientation. This gives you redundancy. The second part is, again, because you have a triangle, you can synthesize a channel that is essentially insensitive to gravitational waves. So you should be, and this is called time delay interferometry, as there are tens of pages of math. I mean, it's not complicated, it's just length. Okay, but the point is, you have channels that should be able to tell you what is the zero gravitational wave readout of your instrument, and then you can compare it to the actual readout. And that is a way to try to discriminate things. Oh, absolutely. But there are people right now that are building a career on these things, and I'm sure 30 years from now they will still be working on try to convince us about something.
It's good reason to live for another 30 years, I think. Another question.
Just a little comment.
Comments are fine.
I never knew so much could come from 3 bricks.
Yeah, well, I think, a lot of the experiments in physics, you can describe them as not terribly exciting. But then if you think about this, what is a telescope? It's a CCD. I mean, but then there is a lot of stuff that comes out of those.
I can ask a question. This is it's not just cutting edge technology, but it's dreamy.
Almost.
Are other detectors? I mean, is the electromagnetic spectrum going to have to catch up with this? Is ESA
okay.
going to push us into a new era of even bigger telescopes, even more sensitive instruments to determine electromagnetic counterparts?
So I think, so in astronomy, as we know, size matters. I mean, you need big things. And in fact, there is this very large ground-based program to build these 30 meters telescopes that will, they will do all sort of fantastic things. But there is also another push, which is to build very cheap, small telescopes, but robotic, that can go after a lot of events in the sky. Because I'm not answering your question. So, there is a big, we've learned that the sky is very dynamic. I mean, 100 years ago, you would point, I mean, the sky is beautiful, but the sky was static. And now there is this, the jargon is time domain transient astronomy. We've learned, for example, from gravitational wave observation, this collision of the two neutron stars, we saw the gravitation from the same sister, the gravitational wave. We saw all the electromagnetic, optical, UV, gamma rays, everything. And we learned from one event, you know, lots and lots of stuff. So there are now big programs for the electromagnetic spectrum to be able to go alongside, for example, LISA. So I didn't talk about this in one of the LISA pictures, artist impressions. I had another telescope, that's the Athena mission of the European Space Agency, that is in X-ray. And the idea is that that mission will fly a couple of years later with respect to LISA, but will be able then to point the X-ray telescope at the center of the galaxies where LISA has made an observation. And, and that will tell us about atoms, molecules, and all sort of mess that happens when there are these collisions. There are these big programs from the ground, LSST, I'm sure everybody has heard about doing this full survey of half of the sky every 4 nights. LSST will be working and, imaging what are the galaxies and so on. So the synchronization of all the different efforts is there, and everybody is really looking forward to that. The problem is that there are a lot of stuff in the universe when you go so deep. And so really trying to identify which little pixel is gonna be corresponding to the pixel that LISA or any other instrument gives is gonna be a problem. So as a comment for astronomy, we are used with the optical or radio or other frequency bands to be able to pinpoint sources. The gravitational wave instruments are all sky monitors. The only information about the position of a source, we get it in the same way as we have position from GPS by triangulation, stuff like this. So the gravitational wave observatories have very poor ability to locate things in the sky. And if you say there is this big patch in the sky at redshift 20, there is a lot of stuff there. Very long answer, sorry.
Just time for one quick question. I think we should let Alberto go.
Sorry, I'll get. Is there any other data in gravitational waves apart from the direction and the frequency? Is there polarization?
Oh yeah, absolutely.
Spectrum?
Yeah, absolutely. So
like a Lyman break, something.
Yeah. So because we really measure a very complex is a time series, and there is let's say a sinusoid with a lot of modulations and so on. Okay. So there is in this waveform a fingerprint about all the physical parameters that describe the source. So there are the two, for a binary system, there are the two masses, There are the spins of these black holes and how they are oriented. And then where is the source in the sky, how far it is, because this is related to the amplitude, and then the inclination of the orbital plane. There are 17 numbers. Okay, in general relativity, if you take a binary, you need 17 numbers to fully describe the entire signal. And in principle, if the signal is strong enough, we can measure all these 17 numbers. It's just 17. Black holes are to some extent, are very boring or very simple. Okay, you need mass and spin, and you describe a black hole, and they are all the same. It's the wiggly line, but the wiggly line of radio pulsars have told us, what fantastic things one can do. So, yeah, well, but it's a wiggly line. It's not beautiful pictures. There is no doubt about that. We're always gonna lose with respect to our colleagues astronomers. Their pictures are so much better.
Good. We have to stop there because Alberto has to go. Just before we wrap up, just to let you know, our next talk is next month. Have I got the number right? I think it's the 15th of February, when Professor Ian Robson will be talking about, get this, Confessions of an Astronomer, which I hope isn't as risque as it sounds, but I did suggest to him we might call it Carry On Astronomer. So that's it for today. Can I ask you to thank Alberto?
No, thank you.
Truly.
Thank you very much. Thank you.